This slide deck will review some alkyl halide nomenclature and properties, as well as get into what is a nucleophile and how to identify them. So an alkyl halide is going to be an alkane where one or more hydrogens have been replaced with a halogen. Now we're going to focus on single substituted alkyl halides, so one halogen per, at least at first. Now we have different classes depending on the halogen atom, the carbon that the halogen atom is bonded to. So here in iodoethane, we have an iodine that's bonded to a primary carbon. We know it's a primary carbon because it's only bonded to one other carbon. So that's a primary alkyl halide. Here in 2-chloropropane, we have a secondary alkyl halide. We know it's a secondary alkyl halide because this carbon is a secondary carbon. It's bonded to two other carbons. And here in 1-bromo, 2-methylpropane, this is a primary alkyl halide, and it's primary because this carbon is primary. It's only bonded to one other carbon. Now we will have some tertiary alkyl halides. Now a tertiary alkyl halide, as you can probably surmise at this point, is a halogen that is bonded to a tertiary carbon. Remember, a tertiary carbon is going to be bonded to three other carbons. So a tertiary alkyl halide and a primary alkyl halide, they're going to be your extremes, with your secondary alkyl halides having the most complicated of the reactivities, and we'll get into that. Now we name an alkyl halide, we can name it with a common name or we can name it with the IUPAC name. So the common name is going to be the name of the alkyl group and then the name of the halogen with "ide." So this would be ethyl chloride. That's common. Only an IUPAC name because we have two bromines. This would also only have an IUPAC name. So for the IUPAC name, we would name it as chloroethane. Whereas this one here, we would count our carbons. So we have a propane, and this would be 1,2-dibromopropane. This compound would be 1-chloro 2, that's an O, iodo-propane. So let's try it. We'll give the common and the IUPAC name. We'll start with the IUPAC name. Remember, in IUPAC nomenclature, we're looking for the longest carbon chain. So you might have to draw out a couple of these if you're in condensed structure and they don't look familiar to you. So here we start with propane. And the bromine is on carbon 1, so this would be 1-bromopropane. For number 2, again, we start with our longest carbon chain, which is also a propane. But this time we have a chlorine on carbon 2, so this is 2-chloropropane. Now for the common name though, common we'll do in red. Common name, we're going to name the alkyl group. So for number 1, I have propyl. And then I would name the aldehyde or the halide. So I have propyl bromide. And for number 2, to name this alkyl group, this is an isopropyl group. So this would be isopropyl chloride. So let's try these. Now we're just doing IUPAC. I'll do IUPAC in blue. I need to find the longest carbon chain. So for this first one, I have 6 carbons. So that means it's hexane. And I have a methyl group on carbon 2, so 2-methyl. But I have a bromo group on carbon 4, so 4-bromo. I have to put this in alphabetical order. So it would be 4-bromo, 2-methyl hexane. For this one, again, you start by finding the longest carbon chain. In this case, I have 5 carbons, so that's pentane. I have a bromo on 2, so 2 bromo pentane. Now, these are just some common halogenated hydrocarbons, and in particular, what I'd like you to see are these chlorofluorocarbons. Chlorofluorocarbons are a big deal for our environmental friends, as chlorofluorocarbons have been used as refrigerants. They've been leaked in the environment every which way, and they are supposedly a cause of ozone depletion. Now, some of the properties of alkyl halides, we have our boiling points. Now, most of our alkyl halides are only going to interact in dipole-dipole situations because we do have some polarity here. We have this polar business here. So we'll have some dipole-dipole interactions. But as we discussed in Module 1, I believe it was, maybe 2, the boiling point patterns will reflect the intermolecular interactions. And I'm not going to go over those intermolecular interactions again, but remember how to determine that. First, you categorize it by the intermolecular interaction. So is it only dispersion? Or are there hydrogen bonding interactions? Hydrogen bonding interactions being the most energetic, dipole-dipole being the mid-range, and dispersion interactions being the least energetic. Then you look at the structures and the molecular weights. Again, I'm not going to go over this again because it was discussed earlier, but the text is there in case you want to read it. Now, generally speaking, alkyl halides are going to be only slightly soluble in water. They do have those dipole-dipole interactions because of that polar alkyl halide bond, but it costs energy to solubilize in water. Water is hydrogen bonded. So sparingly soluble at best in water because we just don't have the ability to solubilize in that hydrogen bonded environment. However, in an organic solvent, we are fairly soluble. Now, the patterns of strength of the carbon-halogen bond follows our reactivity. The weaker the bond, the more reactive. So the stronger the bond, this shows you a strong bond. The stronger the bond, the least reactive. So carbon-fluorine is going to be the least reactive of the halogens, where carbon-iodine is going to be the most reactive. And that's based on the strength of the bond. Remember, we have strength of bonds related also to the size of the atom. The iodine is going to be the larger of the atom. The larger of the atom has a longer bond length. The longer bond length is a weaker bond. The weaker the bond, the more reactive. Now, we know that halogens are more electronegative than carbon, and because of this electronegativity, we have this polar covalent bond. That polar covalent bond yields an electrophilic carbon. It's that electrophilic carbon that we're going to be working with for the rest of this module. Now, as we move up the group of a periodic table from iodine to fluorine, the electronegativity increases, with fluorine being the most electronegative atom. That shouldn't be a surprise. That should be a review. The bond length then will decrease as you go up that electronegativity. So the less electronegative, the longer the bond length. And the strength and the molecular size stuff is here as well. I've said this so many times, I feel like I'm saying it again. But these are important as we move forward. Now, the bond polarity is important as we react. So the carbon-iodine bond is actually not a polar bond. The electronegativity, if I remember correctly, the electronegativity of carbon is 2.55 and the electronegativity of iodine is 2.66. So that difference being so small, that actually falls into non-polar covalent bond territory. But that carbon-iodine bond is a longer bond, it's a weaker bond, it's reactive, even though there's no charge separation on that bond. we're going to look at the replacing of a halogen of an alkyl halide by something else. So we're going to be looking at substitution reactions in Module 4. Now we're either going to break that carbon-halogen bond and produce ions. That's going to be a two-step process. Or we're going to make it push off all at once. So we would have this carbon-halogen bond and we will push it off with a nucleophile all at once. That's going to be a one-step process. So we'll have a two-step process or a one-step process, and I'll show you the conditions for each of those. But what's going to govern that reactivity is the strength of the bonds that have to be broken. Now, you will hear this phrase, it's called a leaving group. So whatever is being substituted or eliminated is called the leaving group. The best leaving group is going to be the weakest base. That's counterintuitive for a lot of people, but the best leaving group is the weakest base, and that's because it's stable. It's stable sitting all by itself. Now, the leaving group ability will increase as you go from left to right across the periodic table and as you go from top down. So leaving group ability increases as you go left to right and top down. So the better leaving group is going to be something like iodine. Now, when you're looking at the pKa of things, a good leaving group is going to have a very low conjugate acid pKa. So something less than 1. Less than 0 is a little bit of a misnomer. So a poor leaving group has a conjugate acid pKa that is greater than 1. Those should be 1s, not 0s. Now we have two different mechanisms. We're going to look into those more in future decks. But SN2 and SN1. The SN stands for substitution nucleophilic. So what we're doing is we're taking a nucleophile and we're coming in after that electrophilic carbon and we are replacing a halogen. So that would be our one step. One step is actually SN2, but we'll get there. You don't have to remember that yet. So we're talking about our nucleophiles. We have to be able to judge our nucleophiles. We're going to have what are called strong nucleophiles and weak nucleophiles. Right now, a strong nucleophile is going to be charged. Right now. And a weak nucleophile is going to be not charged, or a neutral molecule. Now, nucleophilicity is the word used to describe the strength of a nucleophile. So you'll have to keep these points in mind, that nucleophilicity decreases across a row from left to right, decreasing the nucleophilicity in a polar aprotic solvent. Well, what does that mean? Well, an aprotic solvent is something that does not have a proton to donate. So something like acetone is a polar aprotic solvent. Now, a polar protic solvent, then the nucleophilicity goes the opposite way. And we'll get into why that is in the next slide. But a protic solvent is something like any of your alcohols. That's a protic solvent. See that proton right near there, that hydrogen? Water is a polar protic solvent. Your ammonias, that's also polar protic. Nucleophilicity also decreases down a column in aprotic solvents, and nucleophilicity increases down a column for protic solvents. So the nucleophilicity, or the strength of the nucleophile, is largely dependent on the solvent. And the reason for that is because in a protic solvent, the nucleophile will have this cage of solvent around it, and it actually decreases the nucleophilicity. It decreases the strength of that nucleophile because it ties up the charge with those hydrogen bonds. Now, to remember future, and you'll see this again, an SN2 reaction takes place more readily in an aprotic solvent. The rule of the strongest base is the strongest nucleophile will hold, because generally speaking, the stronger the base, the stronger the nucleophile. We went over base and acid strength in Module 1, so that is going to come back now. So these things, whenever you see SN2 or SN1 in this particular deck, know that you will see it again because we haven't defined those completely yet. So as summary, preview, and review, you should be able to pick out your electrophiles. The electrophiles are created with bond polarity, and they are a positive charge, a partially positive charge. Your nucleophile is going to be an atom that has a lone pair of electrons, or it's going to be a pi bond. The smaller the nucleophile, the more nucleophilic it will be in an aprotic solvent. The more electronegative the atom, the less nucleophilic it will be. The more polarizable an atom, so the bigger the electron cloud, the more nucleophilic it is, and this is seen down a column. Now, a strong nucleophile, and this is the preview part, a strong nucleophile will promote SN2 reactions. In this module, that will typically have a negative charge. So here's some examples of strong nucleophiles. A weak nucleophile will promote an SN1 reaction. Again, there's the preview. It's typically going to be a neutral molecule. The solvent is going to matter. A protic solvent will promote the ones because they stabilize the cation that's formed in the ones, and it creates a cage around those stronger nucleophiles to deactivate them. SN2 or E2, the 2s, will be promoted by aprotic solvents, something like DMSO or acetone. There are some nucleophiles that could go either way, so you definitely have to look at the solvent, and these are those nucleophiles. So these are the ones that you need to remember. I would suggest you keep a running list of strong, you keep a running list of weak, and you keep a running list of things that could go either way.